Today we are going to do section 6.8 on page 808, the divergence theorem, which states that if you integrate the divergence over some volume E, that's equal to the surface integral of f over the surface that's covering E entirely. Now let's look at the picture of it and know what we're talking about. See, there is that chunk of package there. That's the divergence. That's the E, okay, with that volume that you're supposed to integrate, whereas the S is the surface, sort of like the shrink wrap of your package, okay? The surface, the exact surface, all the way enclosed, okay, so because being as a solid, the surface completely closed up, and that surface is integrating over that surface of F, that ds is going to be the same as the divergence of f over integrating over the entire E. Now the benefit of this is a lot of times integrating over E is going to be easier than integrating over the surface, which you have to do a bunch of, remember what this means. This means f dot n ds, whereas n is the direction of the surface, okay? So then you have to do that, we have to do tx cross ty, okay, to get the direction and do the dot product. This is often easier, and so we did. That's why we have the divergence theorem. Now to calculate it, I want to remind you of the rectangular and spherical coordinates rules, which will be required when you do some of the homework. Okay, the rules are, you probably remember them anyway. I just wanted to remind you some of it in case. Let's see, what's this? It's focusing. It's not close enough. Maybe I should make it bigger. All right, that is, maybe this is better. And anyway, so the spherical coordinates, of course, has x equal to rho sine phi cosine theta, etc., right? And then the rectangular coordinates down here, which is just x equal to r cosine theta, r sine theta, and so on. What matters is the two Fubini's theorem to do the actual integration of this kind of thing. When you have to integrate over a cylinder or a sphere, it's better to use Fubini's theorem. See? Okay, I just noticed I forgot something. Anyway, so remember Fubini's theorem, cylindrical coordinate is you integrate everything basically about the same, except that the dv translates into dr d theta. So don't forget the r. And similarly, for the spherical coordinates, everything look kind of the same, except that you have rho squared sine phi. Okay, don't forget these two things. That translates into dv. And then everything else will work out as long as you don't forget to this part. But mostly it's the cylindrical coordinate that you should pay attention to. That's most of what the homework is about. Okay, so let me go do something. Now I should mention that divergence, of course, is partial f partial x plus partial f partial y plus partial f partial z. Being that the divergence is stuff that functions that's added up, scalar functions, the divergence is not a vector function. Remember that. It's just a scalar function. Now but it comes from a vector function. F is a vector function with 3 components, but we're just going to add up these things. So let's check the divergence theorem. Is this actually true? For that, please do example 6.77 as part of your homework, where you will calculate this one first, which is easy, and then you will do this part, which is harder and it requires 2 steps in what we did in the previous section. Okay, so please do that, and then let's go to the next example as to using the divergence theorem. Now to use the divergence theorem, we're going to do one thing. We're going to be calculating this, the FDS, but we're going to do it by doing divergence FDV instead, okay, which tends to be much easier because that's all you have to do. The integration might be a little more complicated. Most of the time you just convert it into cylindrical coordinates, sometimes into spherical coordinates, but it will all work out. One thing I want to mention is that your book used different terms. Okay, there are certain things I want to notice. Sometimes your book calls the FDS, okay, the flow rate. Okay, sometimes it's called flow rate, and sometimes it can be called, let's see, that's the flow rate, okay? Sometimes they call it the flux of water. Sometimes it calls it the net outward flux. Doesn't matter what it calls it, it means this thing right here, okay? That is what we're gonna looking for, and that's how we're gonna actually do it, by applying the divergence theorem. So, okay, and one more thing I should mention is that the divergence theorem, it was described as a normal package, as you saw, right? But it is okay to have holes. And we're not going to prove why that is. That's just, we're just going to accept it. So with that, you are ready to do all the examples. Please do example 6.78, 79, and 80. And that makes us come to the end of the section. Now for homework on page 819, please do problems 377, 381, 87, 93, 95, 99, 403, 415, and 423. And for problem 423, please graph it in Desmos 3D so that you see what that volume E looks like. Because without knowing what it looks like, it's gonna be pretty hard to figure out how to integrate it. Okay? Once you see the shape, then the integration becomes fairly straightforward. So please go do your homework, and when you're done, I want to talk about some of them. Now that you're done with the homework, let's look at some, actually all of them is what I did this section. For no reason, actually, they're not even very hard. They're nothing like the one in the previous section, the Stokes theorem. That just took forever. Now, but anyway, I did it, so I might as well show it to you, okay? And so here's 377. We have we calculate something like this. We're trying to calculate the divergence, okay? Take the divergence, do the integration. Being that we're talking about a sphere, we will use the spherical coordinates. And look at what I did here. Check this. I forgot to put in sine phi. So at first I couldn't get the integration to come out. But eventually I noticed the lack of sine phi, and then the answer comes out very nicely. And that's that. So next, let's look at problem 381. Okay, now that is, I think that's the same thing. We have a function, okay? We're going to calculate the divergence, which turns out to be a fairly simple function. This thing we're integrating on a cylinder, so we're going to use the cylindrical coordinates, where we do the integration of the volume, plug this formula, the divergence, inside, okay? And then don't forget that dv becomes r dr d theta, dz, don't forget the r. And once you do that, then the integration comes out pretty good. And that is equal to 12 pi, which is the right answer. So that's that. Next, problem 387, the same thing, I think. Well, anyway, so here you have a function, okay? And then we'll take the divergence, which end up being fairly simple, and then we'll integrate it. Apparently, this thing is supposed to go from -1 to 1, -2 to 2, and -3 to 3. Right. And pay attention to the x, y, z, okay? You're integrating z first, then y, then x, because these numbers are not the same, so you better match it up. So z matches to 3, and y matches to 2, etc. So once that's matched up, you can integrate, you can actually split them up, because then they are breakable, so to speak. So once they're separable, once you separate it, you notice that before you do any integration, you notice that this is an odd function, and you're integrating from -1 to 1, which means this value is 0, and so is this. So in either case, the answer is just 0. Next, let's look at 393, which is, a similar deal. Now this time we're integrating over a cylinder, except the top is slanted. Okay, the top here is some kind of slanted plane. So the only difference then is z. We have the integrate from z goes at the bottom, z is 0. At top, z hits x plus 2. Okay, that's the equation for the plane. So the z's range is from 0 to x plus 2. So we calculate the divergence. We change everything into cylindrical coordinates, except for z's. In cylindrical coordinates, the z stays the same. So then we figure out, remember what dv is, r dr d theta dz. And then so we figure out the limits, okay? Specifically, z goes from 0 to x plus 2, and x is our cosine theta, so you plug that in there, and that's your new range. So you write that down, and then it becomes something like this, which looks like a complete pain to integrate. And I plugged it into the Wolfram Alpha calculator, and so this thing comes right out, see? And that is the right answer. And so next, let's look at problem 395, right? Okay, what are we doing here? I think we're doing the same thing. So in this case, the divergence of f is actually a constant, which means we don't even have to integrate. We just calculate the volume of that sphere, and then that's that, okay? Calculate the volume of the sphere and multiply by the constant divergence, and that is the right answer. So that is the end of that. Now, 399, we have a similar situation. I think, what surface is that? I think oh, I know. I think this is the sphere with a hole inside, I believe. Yes, that's right. So we have, again, the divergence is constant, so we can just take it out of the integration. Here's the sphere with a hole, okay? Here's the sphere subtracted by the hole, and it becomes something like this. Well, it's negative. Well, it happens. And let's not worry about too much what is negative. It's either positive or negative, pick one. And so that's that. And next, let's look at, that's 403. All right, that one, the divergence is, well, anyway, I don't even know why this is, but the divergence of f is equal to that value. You plug it into here, and then I guess all I did, I think I plugged it into the calculator, okay, this whole thing, because well, anyway, I plugged it into the calculator, and then there's your answer. All right, that's the Wolfram Alpha calculator, which I think under my description I call it the book calculator, I believe, because the book recommends it. Well, it used to. I don't think it recommended it in this book, but it's the same book. Okay, it recommended it in Calculus 2. Anyway, let's see. Next, let's look at problem 415. What is that? That is a chunk of stuff. It doesn't matter what it is. We have, so first you have to graph it. Where x is between 0 and 2, the description of the surface, okay, this is actually the most complicated part. And that is, x goes from 0 to 2, and then y will go from x squared to 4. Okay, you notice y goes down to the parabola, right? And then goes up. Up means this direction for y, up to 4. And then z just goes from 0 to 3. So then you plug all these values and the divergence into your integration, and then calculate it. And I don't even think you need to use the calculator, okay? And then the answer pops right out, and that is correct. So that's good. And finally, the final problem, okay? Let me get this. The final problem is, again, we're using cylindrical coordinates. The only hard part about it is that the three surfaces are weird, okay? Now we got more challenging surfaces. In all cases, this kind of problem, the only hard part is to figure out where the surfaces are. So I think these are our three surfaces, and when you look at it, you're like, what is that anyway? So then you type it into the Desmos 3D calculator, and you get a clump of weird looking junk, right? And still weird. The reason is because you got too much extra bits. So what you need to do is get rid of all the extra bits, and then you can see a solid much better. So here is what I have. See, here's the graph of this thing. And please make sure you know how to do this. That is, try it yourself. Okay, try to get rid of all the extra bits. And if you have trouble, look at what I did. But don't just copy what I did right away. first try to do it yourself, and then look at my stuff for hints if you run into any trouble or not sure how to do things. Mostly you just type in the bracelets and then type in the inequalities as restrictions, and which get rid of all the extra bits. And so now we got a cute little thing, okay, that looks much better. And so as you can see, it has the cylinder, the blue one, okay, x squared plus z squared equal to 1, and then the paraboloid at the end there, that is the y equal to x squared, etc. And the plane, the green one, which is just the plane. So you notice the three of them intersects into this thing that looks like, a piece of a pencil stub that somebody cut off. And then so to integrate it, then you will integrate it with the cylindrical coordinates, except that you are going to use y will be considered the new z, okay? Pretend that this is up. So y will be the new z, whereas x and z will be the r cosine theta and the r sine theta. That way, in other words, pretend that you're looking at this thing sideways, okay, where y is now the new z, because and that's the only way to make it, well, make sense, I guess. So here is what I have. See, so originally the cylindrical coordinates have x and y to be sine and cosine, but there's no reason why they have to be, okay? And there's nothing special about x and y. We can totally make it x and z, and then y be the third coordinate. So here is what I did. So we're gonna have x and z to be the r cosine theta and r sine theta, and y will be the one that just is itself. Now to do that, then when we look at it, what are the limits? Then the limits of integration for this will be, as you can see, when if x and z is the new r cosine theta and r sine theta, then theta goes around, is going from 0 to 2 pi, and then r is going from 0 to 1, okay, because the cylinder has a radius of 1. The y is the tricky part. So y will at the bottom goes from the paraboloid, and to the top to the plane. So that's how that's the only hard part of this problem is how y is going to go. So as you can see here, you put y at the bottom is the paraboloid, and the top is the plane. Where the plane is written like this, right? So y is less than the plane, which is y equal to 2 minus x at the plane. So once you have it, this is a paraboloid, the other one is the plane, and together you have the proper restriction for y. Okay, let's see, what is that? And then, and also, of course, we have to translate it into cylindrical coordinates. So x squared plus z squared is r squared, and then 2 minus x is 2 minus r cosine theta, being the x is r cosine theta, and these things, when they're squared, equals to r squared. So now we have it all set. Okay, once we got this integration form details down, then it's just a matter of integrating, which I believe I typed it into the Wolfram Alpha calculator and got this thing, which is the correct answer. And that marks the end of this section.